We have one more week left, so I think you know all the theory that you need to know, or at least you have an idea of how it works and why is it important. And I showed you last time two models, model of natural communication and the glossematics, as models that I believe implement a certain concepts that we as architects need in our modeling, and we currently do not have them. So the question is now, can we somehow implement these models with our computers? How would that work? And this is the topic of today. So this was also a main contribution of my PhD, and I call this implementation of communication models, I call it self-organizing model. And I did not invent this model, so I'm not someone who just took it and now made it from scratch, of course. I combined many things that I learned so far from different people, and also the name. It's more like an architectural articulation, putting more things together in a new kind of, in a whole which is more than only its parts. So it starts with an algorithm called self-organizing map, or SOM. And this SOM is usually described as an artificial neural network. You heard of that term probably, trained using unsupervised learning. So what does this unsupervised learning mean, and how is this, for example, different from supervised machine learning? So let's see what is supervised first. For example, if you have an image recognizer, which of course today internet is filled with that, this is an example of supervised learning. So what you do, you feed your algorithm with thousands of images which contain certain things, and then you label the things. For example, you take pictures with cats and label them cats, pictures with dogs, label them dogs. And then, in the process of learning, computer learns how to associate this label to this kind of data structure that it's present in the image, that exists in the image. So it learns this relation. So what you do then, you give a computer a new image, and then computer predicts a probability of a class. So what is this image? For example, it learned with 10,000 images of cats and dogs, and then you give him an image of a dog, which was not in original data set. Computer should be able to predict that this is a dog. And usually, computers today do this very, very good. Sometimes even 98% correct predictions. So this is supervised learning. But unsupervised learning is a little bit different, because it does not have a goal which you try. So there are no labels that you are trying to kind of predict. What unsupervised learning does is learn the structure of the data itself. So it tries to learn how data is inherently constructed. And this algorithm called SOM uses unsupervised learning. Yeah? And for a long time it was described as a tool for visualization of high-dimensional data spaces. So what does that mean? So on the image you see there, it's an old image. This is kind of how the algorithm was typically used. So what you do is you put into the algorithm certain data which is associated or indicates poverty of a country, so some parameters that would indicate how poor or rich a country is. And then the output is a map like this, in which countries which have similar levels of poverty are clustered together, so they have similar color and they're close to each other. Yeah? So how do you use this? So you look at the map, and then you should conclude by looking at the map, because of the colors, for example, that Canada, Australia, Denmark, Finland, and Great Britain are similar in regards to the levels of poverty. You need to interpret this map. This is how this whole thing started. But before I introduce you to this in detail, I want to introduce you to some very basic concepts of machine learning in general, also computer science, some very basic concepts. And one of the crucial notions in machine learning and computer programming is this notion of data. So let's see an example of how data can be represented in machine learning, and how would we represent a thing that we would like to model as a data. So let's start very simple. Let's say that we have some collection of geometric objects. It can be chairs, it can be any like objects. But let's say that they are objects which we can hold in our hands, for example. And we would like to represent them as data. What does that mean? How would you even approach this? And the interesting thing is that there is no really a single way or the right way or the wrong way to do this, but this depends on what you're trying to achieve. What is your interest in modeling? For example, if size of the object is very important, then you need to find a way to kind of numerically qualify the size. And the simple way of doing that, so you just imagine that you have an object, and then you imagine that you have a box for that object. And this box is the smallest possible box in which this object would fit. Yeah? So you make the box as small as possible to fit the object. This is called a bounding box. And this is a very simple, for example, way of characterizing the dimensions of the object. For example, you here on the image, you have two prisms. And let's say that these are the boxes into which some object fits perfectly. So what you can do then is you can measure these dimensions of the box. Of course, the simplest way would be to measure the length, width, height, as you can see in the image. But also, as you can imagine, if you know width, height, and length, you can also determine the area or the number of, or the volume or stuff like that. But length, width, and height are already included in the volume. So volume is deduced from them. So volume does not tell us anything new about it, for example. So, okay, let's say these are called features. So we decided that our object, we are going to represent it with these three features. And now, if we want this to be, if we want to call these features, and if we want to describe our thousands of objects consistently, we need to agree on one more thing. What do you think this is? It's a very simple thing. Does the order matter here? Order of these measurements. Yeah?
Do we need X, Y, Z axis?
Yeah, just tell me what you think.
I think we need to know which side is where, because the object won't fit if, for example, 80 is not 90 is but 120 in the room.
Yeah. But okay, let's imagine now that we put all of our objects in their fitting boxes. But the thing is, yeah, you need to decide what will be the height, what will be the length, and what will be the width, yeah? And you need to always take measurements in the same order. You always need to compare width with width, length with length, and height with height. Otherwise, it doesn't make sense. They're not comparable then, yeah? So you need to define these features in a specific order, and you need to stick with that. So this is the important part in modeling. You cannot change it. Otherwise, they are incommensurable. You start mixing them together. So if you want to be consistent, you need to take care of the ordering. And now, let me give you an example, another example. On the screen, we have a color picker. You know this from Photoshop, from many other programs. But this shows how color is represented in a computer. So, as you can see, color is a combination of three values. It has three components: amount of red, which goes from 0 to 255, amount of green from 0 to 255, and also the amount of blue. As you can see in the image, we need to put these three values in a list. So RGB, as you can see on the right, there's a function called RGB of three numbers. So order matters. There's a convention that if we want to measure color of an object or represent a color on our screen, we need to take it always in this order. First measure red, then measure green, then measure blue. Yeah? So this is in order to be compatible, that all of our computers can show the same color consistently, and not that in Windows we have red and then you load it in a Mac and then you have green. So that would be wrong, yeah? And now you can see different colors represented as numbers with a certain encoding, which is defined by the ordering. And you can see that red has maximum red component and 0 others. Green has maximum green component and 0 others. Blue has other way around. But then you can also represent any color by a combination of these three. For example, this color is now 152, 88, and 181. Okay, so this is when our computers, when we want to, for example, show colors. But in machine learning, there is another convention that we need to use. Instead of having all these values, for example, length up to 1,000 units, then core 255 units, and all of that, what we do in machine learning usually is we want to have everything in the same range. So we need to compress the range. So if it's something has a range from 0 to 255, what we like to do is we need to squish this range so that this range from 0 to 255 becomes range from 0 to 1. So decimal numbers from 0 to 1. And how do you do this? It's very easy. You just see what's the maximum value. In this case, this is 255. And then divide each of the components with 255, with this maximum value. And then you get red is now 100, green is now 010, blue is 1001. And this random color is, you see, three decimal numbers, yeah? 3 numbers with decimal values. So if you do this with the boxes, then you also need to see what would be the largest dimension of the box. What would be the largest dimension of the box? Here, let's say that the largest one we have is 150 times 150 times 150. What we do is we simply divide each of the measures by 150, and again, we have all of our ranges fit with between 0 and 1. Yeah? And now, there's something called feature engineering. For example, if we do not only want to represent a box, but we want to represent a colored box, we need to encode it in a certain way. So what we can do, we can say that we are now interested for each box, length with width, height, amount of red, amount of green, and amount of blue. So what we can do is just combine these values and put them in a list. And we can take the actual values, or it's better to do it by normalize all the values and then have them all in the range from 0 to 1. And then on the bottom you can see 2 lists of 6 numbers representing now our red box and this magenta, I don't know what it is. Okay, so now you know how this works. So the only thing now, again, the most important thing is that you always stick to this same convention, always in this order. Yeah? So now that you know this kind of intuitively, now let's introduce real names. So these structures into which we put these numbers, into which we store values that characterize objects, we call these placeholders dimensions. So each of these little boxes, we call it a dimension. And this thing, which comprises of multiple dimensions, we call it a vector. So these are vectors. So now our box with a certain color, we represent it as a 6-dimensional vector. Yeah? Do you get it? Why? So vector is a list of numbers, a row of numbers, into which each column has some specific meaning, and columns are fixed, yeah, with the encoding. Therefore, each of our objects, each of our boxes will now have 6 dimensions. So it will be represented as 6-dimensional vector. So now the question is, how would you compare then these 2 boxes that we have here with their features? So for that, we need the idea of n-dimensional space. So we have, you know what is a 1-dimensional space, 2-dimensional, 3-dimensional, but what is n-dimensional space? It's just an extension of this way of thinking. It doesn't mean that we actually have different physical dimensions. These are, so let's call them virtual dimensions. So since each of our objects has 6 specific dimensions, then what we can do, we can take these 6 values to be a point in 6-dimensional space. And in this way, each of our boxes with a certain color will be a different point in 6-dimensional space. Yeah? You get the idea of what does this mean. Of course, you don't have to understand what 6-dimensional space, how it would look like, because we cannot imagine that. But you know what it means. It's the same as in 3D, but it's in 6. Exact that you cannot imagine that, but let's say if we can calculate with it. So how do we calculate then the distance between points in 6-dimensional space? Because if we want a certain measure of similarity, how similar these things are, we need to know how to define distance in 6-dimensional space or in 100-dimensional space. And this is actually not really difficult. You already know how to do it. How would we define distance between 2 points in a plane? What is their distance? Someone wants to try. Okay, I'll go step by step, and then when you see it, then you tell me what to do next. Yeah. So first, we can conclude that there must be a line connecting them. Yeah. This is the shortest distance is the line. Yeah. And then, because they are in 2 dimensions, in 2-dimensional plane, all of these points must have their x coordinate and y coordinate, no? Because on a plane, you always have 2 coordinates. That's the idea of a plane, to have 2 coordinates, yeah? Do you have something? Yeah? Exactly. So you see that this is a triangle, and you know that there's a right angle in the right corner, and you can just use Pythagoras' theorem. What does this requires us to do? We need to find the length of the sides. As we know, the bottom side is simply x coordinate of the right point minus x coordinate of the left point, and the y distance is y coordinate of the b minus y coordinate of the a. Simple, no? So we know these distances, we can calculate them. And now we only need to find the hypotenuse, and this is simple. We use Pythagorean theorem. We know how this works, so you can see it there. So square root of the components squared. So if we just replace, instead of c, a, and b, if we replace these values that we have there, we get the formula. So this is a formula that gives us distance between each points in a plane with their x and y coordinates. Yeah? That's it. So this is Euclidean distance in 2D space. But now to show you that we can extend this concept. If you go to the 3D space, now our Euclidean distance is symbolized by this yellow line down there. So now we have, on top of that line, now we have z coordinate, which points up. And then we need to find this d in the middle, so this diagonal. So what we do, we simply do another Pythagorean theorem to calculate for d. Now again, we have a right triangle. One side is square root of x2 minus x1 times y2 minus 2 y1, and then you have z coordinate, and then you have diagonal. So you just repeat the process. I don't even want to do it because it's trivial. You can do it whenever you want, and you just get this formula. So you get a square root, and then within it you have just differences between each of the coordinates squared. Now the question is, if it's like that, can we then just do this in n dimensions? And the question is yes. It is as easy as that. As you see the difference, now we had 2 terms inside, one for x, one for y. Now we have one for x, one for y, and one for z. If we have n dimensions, we simply need to put n terms. Yeah? So these are 2 points in n-dimensional space. You just need to find all of their respective dimensions and just make one minus the other and square it. And you get to the Euclidean distance in n-dimensional space. So let me give you an example of how this algorithm works now that you know all this. So I started doing this many years ago. I was interested in visualizing the possibilities of parametric models. So you have a parametric model on the screen. What does this model does? You give it 6 numbers. Yeah? It's a program that I wrote. In this program, you feed the program with 6 numbers. 3 are some kind of values related to the shape, and the last 3 values are RGB components, so the color. And then, given these 6 values, this program will draw a shape on the screen, like one of these, and give it a certain color. So now what I did is I made instances of 1,000 of these models on the screen, and I gave them all the random values. Yeah? Therefore, I got thousands of random shapes in random colors. And now I want to show you what this algorithm does. So this is my starting point, this is my input data, and this is what the algorithm does. So what I realized is that this algorithm sorts these 6-dimensional objects and represents them on the screen. But as you can see, similar objects are close together. And similar objects have similar color. And on top of this image, you can also see that if you look not as only at a single element, but if you see a group of elements, you will see that some groups of elements are similar to each other. For example, this thing looks like one of the same kind, so like the same family of things. And this is where I realized that we can think of this self-organizing map as kind of clustering concepts in data. So you have certain concepts in data, like these things, and this algorithm will be able to show you how this works. Now, would you be interested for me to show you how this algorithm works? I can do it here. Yeah? How does this work? Because it's very simple. So, input. So I told you I made 1,000, maybe more, I do not even know, I forgot, of these shapes. And each of these shapes looks like this. You don't even need to know how my program looks like that does this. The only thing you need to know, it takes inputs of 6 numbers. All of them are between 0 to 1. Yeah. So let's say that this is the first one, second one, third one, 1,000th one. All of them have some numbers, 0.6, 0.22, 1, it can be 0.001, 0.3, 0.5. And now this one has also 0.3, 0.6, 0.8, 0.3, 1, 0. And all of them has these values, yeah? And I have 1,000. These are vectors. Vector 1, vector 2. These are dimensions. Dimension 1, dimension 2, 3, 4, 5, 6. Yeah? This is what I feed to computer. What I have here is called a lattice. So imagine this lattice has, I don't know how many times how many fields, but here we will make a simplification. We will say that lattice is like this. This is the size. $11, 77. Here we have 77 cells. Here I have, I don't know, 1,000 cells. Yeah, but it's the same. So what I do is these cells also contain vectors which are of the same size as these ones. Yeah, exactly the same ones. And what I do is I put some random values. So I initialize them with random values. So you get something like this. Yeah. Here I have 1,000 of certain vectors, and here I have 77 of them in this cell. As you can imagine, because they are the same, not same numbers, they are random numbers, they will be completely random. Yeah. Completely random shapes on the screen with random colors. So this is the stage 1. So what I do is I take one of these. Actually, let's make it less complicated. Let's make it that we only have 5 shapes as an input. Or 10. Yeah? Let's less complicated. What I do, I generate a random number. If this is 10, I generate a random number from 1 to 10. And this random number is, for example, 2. So computer, I ask the computer, give me a random number between 1 and 10. Computer says 2. Okay, 2, I take this one. Okay, this vector. Then I present this vector to the lattice. What does this mean? This vector is now a point in 6-dimensional space. All of these vectors here also have 6-dimensional space. And I compare each one of these between each one of these. But these ones are completely random, yeah? These can be my vectors that I like and I know. And these are random. So I compare each one with each one. So I compare it 77 times to get a distance. So If I compare this to this, I get some distance. If I compare this one to this, I also get some distance. So I get 77 distances in 6-dimensional space. One of these vectors will have the shortest distance to this one. So they will all have different distances in 6-dimensional space, but one will have the shortest distance. This one, let's say that this one has the shortest distance. I call this shortest distance vector. I call it BMU, or best matching unit. So what I do then, I create in the simplest case, I don't want to show you how this works on a torus. I will show you how this works on a simple two-dimensional lattice. I make a circle, and I say this circle is in the center of this cell. Then each of these cells here will have a certain distance according to this circle. For example, this one will have this distance, this one will have this distance. So what I do is I apply normal distribution, so I do it like this. The values that are closer to my best matching unit have more influence. So practically what I do is I make all of these things around it a little bit more like this one. So if this one was, for example, red color, and these ones are, of course, random colors, I make all of these a little bit more red. I define, so a little bit more red. And how much more red? This is defined with this curve. The ones that are closer, they get more redness to them. The ones that are further apart, they get less redness to them. So I chose this element, and then now I instructed everything this is within the radius to become a little bit more like this thing. So I transform them so they're a little bit more like this one. And this is done by simple, so you just divide this vector minus, this vector minus all of them, and then just multiply it with a value from 0 to 1 according to this thing. So it's very simple, I don't want to go into that. I just want to give you an idea. So when I did this, all of them became a little bit more like this one. Okay, then I repeat the step. Next step, so this was step number 1. Now I repeat this in thousands of or millions of times depending. So again, I choose a random vector from my input data. Let's say that this time I get 5. Again, I compare this 6-dimensional vector with all of the elements here, and one of them will be the closest one. So let's say that this time is this one. So this is now best matching unit. So what I do, I again make a circle, but this time I make a smaller circle. So I decrease the level of the circle, decrease the radius of the circle. So it's smaller one. And again, I make all of these, which are within the circle, a little bit more like this one. Okay, then next step, let's say I take the fourth one by random, I get the fourth one. Then this one is the most similar to this one. Then I get smaller circle. And then these are influenced, these are not. And these, again, become more influenced. These which are kind of closer to it, and these which are further get less influenced. So I just repeat this procedure thousands of times, depending on the size, and they started organizing themselves. So look at this thing again. This is exactly what happens. It's just this is now, of course, very fast. You cannot see it. But by repeating this procedure many times, they start stabilizing themselves. So it's a very stochastic procedure, which at the end leads to equilibrium, so to say. And you can recognize certain concepts. Okay, so what researchers discovered in the last 10 years is that this self-organizing map is not only useful to do visualizations, but it can be used for tasks which no one ever imagined it can be used. For example, for function approximation. Function approximation is simply you have a certain data set, and then, for example, x and y here in both cases, and then if you have for a given x, you need to predict what the y will be. So if your data is like this is called regression. If this is your data, it's a linear regression, you can, okay, what I do now is I construct a line to best matches this data. Therefore, if I have a new data, this was for my training, if I have new data, new point on x, if this is my x, and I do not know what, I want to predict what the y will be, I simply go to this curve, and this is my y. So this is called linear regression. What they realized is that these cells, if they are represented back into the original space, for example in two-dimensional space, they look like these red points on the right. So not only you can approximate your data, but you can do it very precisely. For example, in the image of the right, data is represented something like this. Yeah. So if you want to fit a line, the best thing you can do is fit a line which looks like this. But then these things are kind of far away, then these are close, but these are far. So this line is not a good approximation of this data. But if you do make a self-organizing map, then you get certain points which closely relate to the shape of the data. So the measure of how closely this mimics the real data is expressed with a statistical value called variance. And on the right, as you can see with this line, variance is kind of high. So things that are unexplainable with this method are, with the line, are 23%, while with SOM, only 6%. So somehow, this tool that everyone thought was just visualization can be used to do function approximation much better than anything else. This is very interesting. So, but what I showed you so far, this is still a kind of classical approach to self-organizing maps. This is kind of artificial intelligence approach. And I want to show you something, how this can be used in a different ways. This was my also research in the last many years. So as I showed you, this is the classical way. This is called feature modeling. You have dimensions, and each dimension represents a characteristic feature. For example, we saw it with length, height, width, color, or whatever. But it can be temperature. It can be also some number that has nothing to do with our physical things. It can be some number that we can derive with some calculations. Anyway, we put it in an n-dimensional vector. Of course, it's never n-dimensional in reality. In reality, it's always a limited vector, limited size. Then what we do, we think that each of our objects is represented as a concept, and this concept has certain number of dimensions, and then we produce a map on the right, which gives us kind of topological similarity. Gives us similarity between these parts. For example, let's see what happens here. What I took here, also as an experiment, is now 9-dimensional data set. So, list of 9 values. 2, 3, 4, 5, 6, 7, 8, 9. Yeah? And what does this number represent? Simply, I made a pattern like this. Geometrical pattern. And I say, yeah, okay, this is a plus. I'm interested in the plus shape. So how can you describe this in 9 dimensions? Simply, you can go like this. If it's white, it's 0. If it's black, it's 1. So then this would be 0, 0, 1, 0, 1, 1, 1, 0, 1, 0. Okay. So now I put a lot of shapes. I made another one. I made a diagonal. Now this diagonal would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah? So I made a lot of them. And then I want to see how the self-organizing map does it. Again, this process here. As you can see, it organizes the shapes according to the similarity in 9-dimensional space. But we are able to visualize it because all of our patterns can be represented as 9-dimensional vectors. because there is a geometrical interpretation of any number here in 9 dimensions. There is a geometrical representation in 2D. Yeah? But now, let me show you the different approach that I came up with. It's still kind of ongoing research. It's a quite different approach to self-organizing maps, and it's based on a kind of completely different assumptions how we should represent phenomena. So now, I do not want to represent an object to say that a red square is 6-dimensional vector with width, height, length, and red, blue, and green. I want to say that I have certain measuring devices. Yeah? And there is something in the world which is observable that I can measure. I simply take these measurements, of course normalized between 0 and 1, and I stack them together. And each of these numbers will give me a kind of local geometric spectrum. But also when we take them together, I will have kind of a list of different local geometric spectrums according to how many observables I have. So practically how this looks like, I have a number of observables, for example, 1,000. Then I need 1,000 measuring devices, or whatever number. Yeah? And I simply, each of the measuring device, I feed it in a certain dimension. So for example, if I have n-dimensional vector, as you can see on the image, dimension 1 will be measuring device 1. Dimension 2, measuring device 2. So measuring device 1,000, dimension 1,000. And then what I do is I introduce time, and these measurements are happening in time. I just discretize time, and in each second or millisecond or whatever, I take one measurement, and this new measurement becomes new row, becomes new thing here. Yeah? So what I have now is my measuring in time of different observables gives me sum. So this is then a list of values like here, but gives me a sum which is itself a concept, not a map of concepts like we had before, but a concept itself. So let's look how this looks like. On the left, we have an example of concepts of sum. So I take my objects, I define their features, and then I put them on the map, and then the sum shows different concepts on this map. But now what I do is I measure in time. I take each of my measuring instruments as a dimension, and I take the data as kind of sequential measurements in time, and I get sum as a concept. So I inverted it. Concept of sum as a concept. Yeah? But of course, this sum as a concept that you can see here does not really tell you that much. You don't know what to do with this thing. You do not know what it means, because it cannot be visualized. So it does not communicate any information. And also, to make it even more difficult, every time you make a sum, you calculate a sum from this new kind of, for this new kind of object, you get different results. So as you can see, all of these images on the screen are kind of similar to each other. You would say that they are just kind of in the same family of things. They have similar boundaries, similar sizes of certain clusters, but they're different in geometry. Yeah? So if I want to compare these two computational concepts that are now more abstract than what we had before, I need to define that these things, the distances, I need to make my model such that these distances are made zero. So if we take two computations out of a single object and we have different instances, different geometrical instances, I want to make sure that distance between them is actually zero. So I need to assert that in my model, distance between two computational concepts of the same thing should be zero, although they do not look differently. And this is a very complicated thing to do, to establish a notion of distance to be zero in this case, because in this case we can imagine that the elements within this map, these little cells, are the same elements, but they are arranged differently. So how can you then approach this problem? You can say, okay, I have these measurements. I need to find a way to measure them without this arrangement, without the context. But then the problem is, even if you have a very small cell of four elements, sorry, this should be ABCD, not ABCC, ABCD. You can see that these 4 elements can be permuted 24 times. So from 4 elements, arrangement of 4 elements, you can have 24 arrangements of them. So now if you have n times n, you can imagine that this number grows very much. And in fact, this is called a factorial growth. So if you can see that, for example, cell which is 2 times 2 has 24 combinations possible. If it's 3 times 3, it has 300,000, yeah, around 300,000. And if it's 4 times 4, it's like 20 billion, I do not know. Yeah. So this is not how to solve this problem. This is a very difficult way to solve this problem. So what I did, I used methods of combinatorial optimization, and I was actually able to solve this. So what you will see now is I will have now 2 self-organizing maps. So 2 of these. Let's call them A and B, each of them describing a certain concept. So this is concept A, concept B. And I need to find a way to establish distance between them. What would be the shortest distance between them? Now, they are very different objects. They're not anymore points in n-dimensional space. They are actually aggregations of points in n-dimensional space, which is much more difficult to calculate. So one will be described with blue dots on the screen, and the other one will be described with the red, which I do not have, unfortunately, but I just imagine these are red. So, as you can see now, I'm putting first points of one self-organizing map on the screen. So imagine that actually this is computed, that I'm not putting them. And in this case, it looks kind of easy. What would be the shortest distance between all of these points? So I need to minimize the overall shortest distance between these 2 groups of points. And in this case, this looks like, okay, it's complicated, but it's kind of understandable what this might be. But to show you that this is not really like that, in a real-world scenario, these points will be mixed in space. They will not be forming certain lines, but they will be complete mixtures. So one of the one sum, one of the other. So I'm adding now points here by hand, but imagine that the computer does that. Now, as you can see, it's a very difficult question to determine what's the overall shortest distance. And I found a solution for this by using so-called Euclidean algorithm. So you need to find overall 2 points between 2 groups which have the shortest distance between them. Yeah? And now, once you can do that, then you can find the distance between 2 computational concepts. But now let's see what a computational concept can be. It can be whatever, but let's take an image to be a computational concept. Yeah? So I want to show you more intuitively how this works. So now, this image has 4 megapixels, which means 2000 times 2000 pixels. This is 4 million pixels. For each pixel, I can detect 2 values. One is, for example, what is the, if this is an image, and this is a pixel, I can say that this pixel is 40% of the width and 50% of the height. So this will be 0.4, 0.5. So relative position according to the, for example, coordinate axis here. And each pixel has R, G, and B values. Yeah? So this means for each pixel, for 4 million pixels, I have 5 dimensions. So 20 million data points in 4 million data set. Yeah? So what SOM does here is organizes these pixels. And then you see the spectrum on the right, and you get some boundaries. You know this from this image from before, this where I showed you in the first example. Now, for each of these SOMs, if I move around inside of them, each of these regions will represent a certain pixel of the image. So, for example, sky will be represented by one region. For example, the one on the right will be sky. Some other will be tree. Some other region will be the facade or windows. So these all elements are now kind of in a certain data landscape on the right, which has certain boundaries and certain regions and so on. So what is black on the region is the boundary. So if two objects have sharp boundary between them, they're black, and ones that have white, they're kind of similar to each other. Yeah. So now this is, for example, concept A. And now let's do it for the concept B, which is also an image, just a different image. Yeah. So now let's do the same process on the second image. I repeat this, I don't know how many thousands of times, until it stabilizes, because this radius is always shrinking. Therefore, this stabilizes at the end. And now, when I move my mouse on the region on the right, again, this will correspond to some region. So sky will be different than the forest, and different than the roof of the house, and so on. Okay, this is now B. Later I will show you how to then calculate how similar these pictures are according to these grayscale images on the right. But now our computational objects does not have to be an image. It can be literally whatever. So let's do it from let's extract some information from a 3D model. So I went to a Google 3D warehouse library. I downloaded these models, and I just took X, Y, and Z coordinates of each vertex of the model. I didn't even bother with phases, just took the X and Y, Z coordinates of the vertices. And I trained my computational concept of this chair. As you can see, this is what we get. So this is the kind of concept of this chair in terms of data. Of course, this is now visualizable because it's 3D and the images are 2D, but you can now imagine, in the same way we did before, you can do this in n dimensions. Therefore, you know what you will get intuitively, but of course you do not know how this looks like. This does not have a form in physical form. But you know that if it works in 2D and 3D, it can extend to as many dimensions you want. It's just you will not be able to see it. Yeah? Then I do this, used self-organizing map to do time series prediction to, for example, predict what will be the next value of the stock market and stuff like that. Or now let's go to how can we actually find distances between two images. So there's a guy called Kalev Letaru, and he's a researcher who extracted 14 million images from 2 million books of Internet Archive and put them all made them more available. And I took 2,500 to test the similarity. So now all of these images, I calculated a sum for each one of them. Yeah. And now I use it almost as a Google search. I say, this is my question. This image is my question. Now, according to the similarity between the two images, according to these 5 dimensions, give me the most similar images sorted by similarity. So then I do this operation that I show you, and I found the distance between each of the images with this one. And I get, in a folder, I get these images like this. So first one that I get the most similar is the image itself, because it has the distance 0 to itself. Of course, each image has 0 distance to itself because it's the same thing. But let's see what the other images are. So this is what I get back. So these are the most similar to the one that I asked out of 2,000, 2,500. And these ones are the least similar to them, according to my 5 dimensions. Also, what I did is I made character recognition software with the same algorithm. So I would write I literally write letters with data points and get a sum for each of these data distributions. You see, for B, for A, B, for C. Yeah? And now I'm asking, what is this? Where does this correspond to? And it tells me A. So because it's the most similar to the first one. This one will be B because it's most similar to the second one. And this one should be most similar to the third one. You can use this in many ways. I was, of course, just playing. Yeah, but my idea was, yeah, how to then formalize this procedure mathematically. What would be the what would be kind of the algebra? Can you make a mathematics on top of these structures? I was playing a little bit. Of course, I'm not a mathematician, but I kind of discovered some properties. For example, first property is that distance of each element to itself should be 0. And then commutativity I also discovered, because distance from this one to this one is the same as this one, distance from this one to this one. So therefore they're commutative. And I've also found some different mathematical properties which I don't want to bother you with. Then I found another way of improving this algorithm, which is known as growing neural gas. Now the idea was that not only I want to have a certain number of that I do not only want to represent my object with a kind of fixed structure, as this lattice, for example, but I would like to grow my model such that it adapts to the data itself. So now this model learns how to represent this image, as you can see here. And this was a challenge because there was a paper, but it was really I could not find really implementation on the whole internet. I could not find an implementation of this. So I did it myself. It took me some time. I want to go into details again. But yeah, I implemented this. So if this is my data, these points around the circle, and this is my structure of points which will need to adapt to represent this circle. I discovered some certain mathematical properties. For example, instead of this best matching unit, I also have a kind of best matching unit which I hold signal here. I presented it to my red data points that are trying to mimic the gray ones. I calculate the distortions or the distance between them to the signal and then sort them. Then I'm trying to visualize these distortions. It's a little bit difficult to watch because I don't have it on my screen. Adapt it to be more similar to the ones that I selected, as you can see it here. I don't know if you can see it. No, not yet. So I calculate the distance from this point to each one of the others. Then I represent, for example, my input data as Voronoi cells. For example, each of these gray points has a Voronoi cell, and also each of the red points has a Voronoi cell. And the interesting thing is, this is a mathematical property, but if two cells are closest to our signal point, then these two cells, Voronoi cells, should be connected. Therefore, these two objects should be connected. Then I made the connection matrix. It doesn't even matter. I just want to show you how it looks like. I'm not sure what's going on. Yeah, these are all possible connections. Then this is the how things, you know, how I showed you here, how things which are closer to the best matching unit, they get more like the point. They get more like a best matching unit. Here, the points that are closer to the signal, as you can see here, this is quite close. This point becomes more like a signal. So if this was the old point, the new point will be here. But if they are far away, then they will be less adapted. You see, this one is pretty far, and in terms of its length, it's less adapted to the signal than this one. This one is kind of more, and this one, of course, much more. And then you just repeat this procedure, and you can see that the data starts to connect now. You see, starts expanding, expanding, expanding. You see each, I don't know how many, 50 steps. Oh, 200 steps. In 200 steps, you see how this thing grows. And at the end, you get this. It's kind of, with this small amount of points, we are able to approximate this circle made of gray points. But let's do it with a more complex object. Again, this is the process, how it works. I do not have time to go into detail, but you see a process, how this is done. How it learns, and at the end you can see this is our original data, and this is our approximation with a limited number of points. Yeah. Okay. We are closing and going to the end. What I realized is, of course, working with the algorithm, but also working with the model of natural communication that I showed you last time from quantum physicist Elias Zafiris, is that these two architectures, or architecture of the model, of the algorithm, and architecture of the natural communication model are kind of similar. So I superimpose them on top of one on top of each other. So on the right, you can see the self-organizing map shown on a motivic key of natural communication. So what I realized is there are 4 parts that this algorithm can really be described by the 4 elements of this key. And then my colleague Vahid Mosavi, he made a table of references about this algorithm and all of the improvements and all of different applications. And what I realized is that all of these people who improved this algorithm or played with it were kind of making a use on one of these properties of this key. So either they will improving the top part or the lower part, or the mapping between them, and so on and so forth. So what I did is I then created my own key and named it a coexistence key. And this key generalizes the self-organizing procedure on the basis of models of natural communication as glossematics. So now what I realized, how I made this model, is that it has 2 models. It has domain A and B. Yeah? In the domain A, we have our data or observables. So we have our data set, which we measured somehow. But of course, this data set has some meaning. Stuff that we observed, stuff we measured, have some meaning. But the meaning is not necessarily in the data. Yeah? So we do not know what it means. So what we do, we would like to observe what happens on a different level of this model. And to get there, we need a generalization procedure, which I took from the self-organizing map. So a generalization procedure which encodes our set of observables on the level A into a topological structure on the level B, or more speaking more generally, I would call it, what we have on the B is a kind of self-referential system of node and arrows. I don't want to say that it's a structure like this, because as you have seen, it does not have to be structured like this. It can be a kind of very free structure, like I showed you the last time. And I call this a category. So if we cannot solve something, if we cannot represent something and solve it on the level of data, like we usually do it, with some data we try to understand what it means, what we can do, we can translate it on the level B, which is this more abstract structure that I showed you so far. Over there, we get a different context. Our data sets are now represented in a very different context, and we start to understand something about our data. What is similar, what is dissimilar, what has a boundary between, what is in the same class, you know? And then we might be able to solve our problem on the level B. But now when we solved it, we need to translate the solution back to our original data to know which of our objects, which of our shapes was, for example, a solution, because we do not know it on the second level. Yeah, this is a simplified way of explaining this. I will explain it in more detail next time when I show you the actual experiment. So practically we have communication between the domains A and B established by these two procedures, generalization and projection. And for the generalization procedure, I showed that we can use self-organizing map, or, for example, neural gas, or different networks. In this way, I'm showing the algorithms of machine learning in context of kind of mathematical, in a mathematical context, in terms of category theory. And I see it as a kind of direct representation of processes that and models we use in physics. So what I've shown you so far also can be kind of crystallized in this table. I recognize that we might be better off by using a language model such as glossematics than what we usually can do with linguistics. Then instead of having simulation models, we are better using communication models. Then instead of using kind of single level hierarchical structure in modeling, it would be better if we could stratify our model between multiple levels and enable communication between them. Instead of thinking about our objects as kind of clearly defined crystal structures, we can think of them like things which emerge from indistinguishability, like some kind of temporal foam which can have soft boundaries, but also hard if we want to, as I showed you on these examples. Also, I recognize that we would be better off using category theory to describe these processes and phenomena than set theory. And coding is not anymore about grammars, but it's about geometry. And also, this renders machine learning from this idea of neural networks that I showed you in the beginning towards a kind of coexistence in the world of data. So we are interested how our data can coexist on multiple levels. Do not see it as a single given thing, but how this kind of representation can coexist in multiple levels. Yeah, so that's it for today. So if you have questions and if you would like to know more how certain of these steps work, or if you want me to repeat, feel free. I'm open to explain everything in detail, however you want.
Could you please show again one of these self-organizing maps from the beginning with these shapes and colors?
Yeah. This one.
This one. I'm wondering what happens if the distribution at the beginning is slightly different. Does the result is the same, or?
If the distribution in the beginning is very fixed,
Yes.
it might be that the algorithm will have some more problems to decompose it, because, for example, BMU, you imagine, so what happened is, first step is I find a random input, so random shape, and I present it to the whole lattice. And then I find where is my best matching unit. But if data is not random, if it's really already pre-organized, then my best matching unit can be distributed in one and the same region. So then when I do my first step, they will be always within a region which is already kind of very compact. While in this case, it will jump around. Therefore, if the data is already compact, then my circles will kind of jump more towards these regions which are already compact. So it will take longer time to decompose the thing. And in the same amount of time, it would be better result if we start with random than if we start with something which is already fixed. Yeah?
But the result is not always the same.
No, it's always different. The relations between these abstract cells are the same, but and the values of them are also almost the same, but they're arranged in a different way. This is called the idea of isomorphism, that things can look the same, that things have same connections, but can be represented differently. Let me see if I have an example of that.
That's not true with the example of the image, right? There it stays the same because we have the same boundary condition because the coordinates of the fixed point are also a criterion.
Yes, but in the image, what I did not show you is that image are very concrete and very kind of, how to say, ordered image of pixels is now in input. And from input, we select randomly. Yeah. So we decompose our input, which is a 2D image, in one huge list of 4 million pixels, and we choose by them randomly. And on the right side, we start again with a completely random pattern. So in this sense, we do not have a bigger chance of landing to the same area like what he asked, because this is a kind of different approach. First one was concepts within a map, and the second concept was map as a concept. So in this second case, you do not have that problem. If this is what you asked, maybe you actually asked something else.
The second, with the image, you're also looking for which is a criteria for the mapping, and in the first one, it can also always be a different distribution. Is that true? So is the blue data mapping of the image we've seen always on the right corner? Is that the question actually?
No.
I don't think so.
Okay.
No, it doesn't have to be.
Then map it in a square and make the relationship circular.
This is what I actually did, but this is not possible to visualize. I did not actually, in my examples, do it on a square. I mapped it onto a torus.
Okay.
And you know how torus looks like. And how to make a torus is quite simple. It's just you need to connect this one to this one, this one to this one, and this one to this one. I mean all of them. Therefore, this is the neighbor of this one. This is the neighbor, and this is the neighbor. In this way, toroidal data. It does not at all. Sorry?
That would have been my next question, but it wasn't.
It was, but how to represent a torus? I mean, of course, I can represent in 3D, but you can just imagine. So what happens is, just let me find some examples here. I have examples for all of your questions, so just so far your questions, you can find them. No, we're just problem to find them now. Oh, exactly. Isomorphism. Actually, I do not have to. As you can see, this structure is isomorphic to this one, so we do not change the connections at all, but we get completely different shapes while stretching them. This is the idea of isomorphism. This is what happens with these maps. They look different, but only because they are in different cells. But their connections are kind of the same. So this is the problems we are facing, always. Yeah? And your question I also had. Ah, yes, torus. Well, I do not know where it is, but let's make an experiment. So if it's torus, I do not know if this exact one is a torus, then it should be able to tile. Actually, let me check. I do not see my cursor. Should be able to tile it. It should continue. But right now I don't see it, if it's really. It should be continuous if it's a torus. Of course, you cannot ever show it. Oh, it's not very. Yeah, if it's a torus, this pattern should be uninterrupted, and in most cases it is. It's just I do not have a better way to represent a torus than as a kind of 2D image which is repeatable in X and Y. I will find more images, but I don't know how much time I have. I mean, I don't want to bore you with. Maybe I have more. Yeah, I cannot find more images, but I was playing with that. But this is, for example, an idea of how you can construct a torus when you're looking for these circles. On 2D plane, then this circle would, of course, take this data which does not exist, yeah? So this circle would take something which is not there. But if you see in torus, if you have a circle, you need to make 4 copies of circles, and each one of them takes one region. So only the thing in the middle is this lattice, and then this lattice is copied because it's connected. The one above is the same as one below. Therefore, you need to make four of these circles in order to compute a torus. It's a little bit more complicated, but once it's done, it's done. So. Any more questions?
Can you show the 9-dimensional?
Oh yeah.
What I find confusing if this is a torus is why the bottom left is all black and the bottom right is all white. Because if they are like connected to each other.
This one is not on the torus. These are the early experiments that I made. Yeah. So this was 2006. No. 2016. No, maybe even before. 14. Yeah, but back then I did not do it. So if you do not do a torus, then this is what happens. Yeah. This one is definitely on the plane.
And is there gray because you use 0, 1, and 2? Because, I mean, we have white,
Yes.
gray.
Here I'd used 3 values. I used 0. Yeah, I normalized the values, all that come in between, to either flip to 0, to 1, or to 1/2, so that you have middle gray one, white and black. Yeah. Otherwise, what would happen is you would have an image which is completely black and white, completely grayscale, because all of these translations from one element into each other will be done on the grayscale level. So here I did not make it that visible, so I put only 3 levels, so that you can imagine still where the transition takes place. Yeah.
Right now you're working with a 2-dimensional relationship, right? So you're influencing in a circle. What would happen if you would influence the other points with another influence rate? I would say more linear and a little bit circular, so like in a oval more or less. Would this help to compare images and find boundary conditions?
Well, that's difficult to say, what would happen, because you don't even know what happens in this case. You kind of have an idea, but you cannot exactly predict what is going to happen. This is the thing. It's kind of probabilistic thing because it's based on stochastic, on random distributions and how these random distributions converge when they're pushed by something else, by certain forces. But what is important to see is that here, this circle, this does not mean that I am somehow compressing my data into 2D. What you need to understand that each of these elements on a grid, this is not a geometrical structure. This is a topological structure, which means there is no measure, there is no relation, there is no distance between them. The only distance between them is if they are neighbors. This is distance 1. If they are like this, then distance 2. But there is no measurement of like 0.3, This is topological. So this is a topological structure. Within each of these cells lives 6-dimensional object. So how I'm adapting them with the circle, I'm adapting topological relations to put them together. But the objects are actually dancing in 9 dimensions. But I cannot represent them in 9 dimensions or 6. I can only represent them in a 2D lattice. So this is kind of a scaffolding that is used to represent this.
I mean, you could also represent them in 3D, right?
Exactly. I could make this lattice into a three-dimensional lattice, which will be something like this. Of course, their points would be here. And then, in order to adapt them, I would not be able to use this. I would need to use a sphere. So I would use a sphere to define an influence between points. Yeah?
Then you would generate even more complexity in the boundary conditions.
Yes. Then I would have 3-dimensional boundaries.
So my question was, could you present it? You can't present it in a 2-dimensional space, but in a more 2-dimensional space. So it's more comparable. It looks more comparable because you're heading towards a 2-dimensional space because the 2-dimensional criteria would get more important than the 1-dimensional would be more important than the 2-dimensional in the representation.
I'm not sure if I understand completely, but
Like if it wouldn't be a circle but an oval,
yeah.
the criteria in one dimension, in one direction, would be higher than in the other one because the oval has axes.
Yes. So obviously, if this was oval, organization
Would be in layers in the end.
why in layers?
Wouldn't it? Like it would with layers somehow. And form other. I'm just thinking about other getting other boundary conditions to compare it in a simple way.
Yeah, you can use many boundary conditions. Here, it's easy to use the sphere, to use the circle, because it's kind of in 2D, and circle in 2D. What circle means? Circle is concept that all of these points have equidistant from this point. Yeah. So if then we are concerned by this element, then this equidistance treats the whole 2D plane equally. So does not say that x dimension is more important than the y in this context. Therefore, we use circle. If we use the oval, we would assume that one dimension of topological dimension is more important than the other. And I do not know why I would like to make this assumption. That's why I don't do it. Because I do not know why would I want to have a preferred topological dimension instead of the other one. So I treat them equally because circle does it equally. Yeah. But of course, I'm not a researcher. I didn't invent the algorithm. I just tell you my intuition why. But yeah, for that question, you would need to ask the guy who invented it. I can just tell you why I would use it or not, in a certain way. In the way how I implemented it with this neural gas that I show you, it's a different way. Over there, if we had a BMU, which is best matching unit, which is this thing, and then we had data around it. Of course, now this is in n-dimensional space, but yeah, there's no other way to talk about it. Adaptation was different. Adaptation was not done by making some kind of sphere in 8 dimensions, but it's done by making distance from each of the points. And then, if the point was closer to the best matching unit, influence would be bigger. If it's further away, influence will be smaller. So what then happens in an adaptation stage, this point gets a little bit closer to this one. For example, 20% closer, while this one will get only 5% closer because it's further away. So that's another criteria which is kind of similar to this, except here we do not have a predefined structure so we can use a circle. Here we do not have any structure. We do not have connections between the elements yet. Therefore, we use everything according to the relative distance to this point. And then we define, according to how they are connected, the 2 points that are closest to each other will actually belong to 2 Voronoi regions that are adjacent to each other. Therefore, you should be making a connection with these 2 points. And then this is how connections grow in a bigger picture. I know this might be a little bit complicated if you see it for the first time, but I think actually it's not really complicated at all. It's just you need to think that 2 dimensions, 3 dimensions is the same as 100 dimensions. I mean, the same thing applies. You can find distance between 2 points in the same way. It's just you do not see it, but you know, who cares? Yeah.
I think if you value one component of the topological space more than another, what happens in the other? Then you just falsify the result because it becomes stretched. That's my assumption, because when it's a circle, every distance is the same. When you give one the x value more, you think that's more important, or it should be factor 2, then the whole thing stretches, but it doesn't show anything more in the stretched result, I think.
Yeah, probably the results become stretched in a certain way. The whole topological, this thing called the manifold becomes stretched, I guess. But I don't think it's a different, yeah.
I'm just imagining there are photographies from, I think it was Tillmans, who didn't make a point in his camera, but a line, and so he got pictures which were layered, only layers. And this, in my mind, I see more structure within this presentation, and that you wouldn't have the problem with when comparing with the whole complexity of this circle, which was implemented in the start. I know that the other would probably implement as much complexity, but I'm not sure. I'm just thinking of something. I don't know.
Okay, I'm not always able to, we might be talking about completely different things or completely the same thing, but yeah, it takes time to tune, to really understand what the other person means, especially when we are dealing with very new ideas here that you probably have not seen in this detail before. Or maybe you just know that it exists, but didn't know how it works. And yeah, of course, there can be very good, all of the questions are great questions, and this is what I like to hear from you. Because I do not expect you to know, for you to be experts that are now gonna know this. I mean, I also do not know. I have an idea what it is, but no one really knows these things because these processes are not deterministic. They are kind of probability based. They are stochastic. They are based on the probabilistic distribution of your data, then on the stochastic choice of these vectors. You do not have an exact solution there. You have a kind of sketch of a concept, so to say. Yeah. Anything else?
now I think it already becomes a concept. Or what's the difference between this and the concepts you, in the last part of your lecture, try to compare? This one with the lines now. Here there would be black lines, thick black lines, because there's a big difference, and maybe here.
But I made the black lines, yeah. So I did not. The program did not find the black lines. I said, to me, this looks like something, you know. So there's no clear way of saying where's the boundary. You know, boundaries are porous. They have holes somewhere. You know, they're not set theory like it's this or that. It can be both. So this is kind of what we say, that machine learning is kind of reflecting the quantum paradigm of thinking, because it's of course not quantum that's going on in the computer. Of course, some things are, but that you're not sure exactly if it's if it's open or it's closed. It's both. You know, depending on how you see it. Of course, this one region is very prominent, but not all of them are. You cannot make this one is more, as you can see, each geometry also dictates that it's quite different than the others. While the others, which are, so if you imagine this as a kind of a map, imagine this as a map looking at from the plane. You can imagine that there will be some huge ridges on these things, and there will be a valley. If you think about similarity on top of this, then there will be a valley in the middle, and then will be like a volcano. You know, this will be like a volcano. You know, you will have some boundary here, and then something down there. Of course, these sides, I'm not sure how would they look, but this is what you see here. You see that here in the middle, everything is kind of the same. Then there is a clear boundary where it becomes something else, and then the rest is kind of blurry.
No, this is in geometry. And the concepts are in topography. The ones of the images.
Yeah. What is kind of misleading here is because here we have topology and geometry on the same image. Because I'm able to visualize these 6-dimensional objects by making a shape out of them. But in data, it's not always possible to do it because, yeah, how can you visualize? You have 100 numbers, how to visualize 100 numbers? You have no idea. Especially if it's a measurement, you know. Now I made a program which creates shapes out of 6 objects, therefore I'm able to visualize. Yeah. You also wanted.
I just want to point out that I think that this region, points out to us. I think that's our own misinterpretation, because these objects, they are so small that we can't differentiate the colors anymore. So I think like if they were bigger, it wouldn't be such a big region.
Exactly, that's a good thing. That's a good thinking. What happens here is that certain dimensions on this image are more pronounced than the others. So it might be that if we were able to see it, there will be different colors of these lines inside. But simply because one dimension here is so dominant, we are not able to even see it exactly as. But still, I would still say that looking at this, it's still, you can recognize that it's a different concept than what is around it. Even though you do not know what's the color. Yeah, but then what this model of natural communication does that we showed before, which kind of, in my opinion, very well complements this schema, these 3 parts, is that this process in the middle can be repeated. So now you can take the middle part and make a new self-organizing map just on the middle part, and then see how this part can be decomposed into different regions, and then you will get something differently. Again, as you very well noticed, now the geometry is not allowing us to see the color. That's why we should not always trust visualizations. That's why I decided to represent things not as objects, but like this. Because here, you have pure difference between these cells. So what you have here is each of the cells, what is represented here. I calculate the distance between its cell and its neighbors. and I make an average of the distance between each cell and its neighbors. And if this number is high, this means that this particular cell is far away from its neighbors, so kind of elevated, let's say, or like a ridge. And if it's white, if it's low and white, this means that the distance is kind of low, which means that they are in the valley or they're on the same height. So if you see this as a kind of some kind of map, then you would definitely see that these are peaks of the mountains or some kind of ridges. And then you do not have these confusing things that geometry does. So here is pure topological description. And I think we as architects, we need to trust in these things, because if we are in hundreds of dimensions and of thousands of dimensions, if we want to think on a very abstract level, we cannot trust always geometry, because it's simply not able to show us. We should learn how to deal with these topological ideas. Something else? I'm very glad that today you asked a lot of questions and find a lot of interest. So if there are no more questions, then let's finish for today, and yeah, one more class and we're done. Thank you so much.